For decades, the idea of a warp drive has pretty much lived in the realm of science fiction. But back in 1994, a physicist named Miguel Alcubierre showed that, according to Einstein's General Relativity, the concept wasn't just fantasy. The math actually worked. But there was a huge catch. It required something called negative energy density, a type of exotic matter that probably doesn't even exist. And for a long time, that's been seen as a physical dead end. But what if that core assumption was wrong? In this explainer, we're going to dive into a thesis that re-examines the whole problem, asking a really fundamental question. What does the math of relativity actually demand from us?
So, here's our roadmap. We'll start with the classic warp drive problem. Then we'll see how this new research tried a totally different approach. We'll look at the math they ran and the pretty surprising things they found. After that, and this part's crucial, we'll talk about what this theory doesn't prove. And finally, we'll explore where this new path might lead. All right, let's nail down the core challenge here, the thing that's had physicists stumped for about 30 years. It all comes down to general relativity, which is our best theory of gravity. It tells us that mass and energy literally bend space-time. And, well, the theory allows for space-time to be bent in some really weird ways. Now, the Alcubierre idea is just brilliant. A warp bubble doesn't work by pushing a ship through space faster than light. No, it moves space itself. It actually shrinks space-time in front of the bubble and stretches it out behind. The cool part is, the ship inside is basically just sitting still in its own little patch of space, so it never locally breaks that cosmic speed limit. But the bubble itself, riding this wave of space-time, could theoretically travel at almost any speed from an outsider's perspective.
Okay, but here it is. This is the big one. The roadblock that stood for decades. To get that very specific curve in spacetime, the math absolutely required a source with negative energy density. Now, this is not antimatter. It's something totally different. It's a hypothetical material that would have repulsive gravity. It would literally push things away. The problem? We've never seen anything like it, and it seems to violate some fundamental principles of physics we call the energy conditions.
And that question brings us right to the heart of the research we're looking at today. You see, for years, everyone just assumed you needed this exotic matter to even start the conversation. But this research asks, do you really? Is it possible that the geometry of a warp drive could be held up by normal, conventional sources of gravity?
So this is where the objective of this whole study really comes into focus. Instead of just accepting that exotic matter as a must-have, this thesis completely flips the question around. It asks, could the Alcubierre warp drive geometry be created by forms of matter and energy that we actually know and understand? So the researchers modeled the source of this space-time curve using things that are, a bit more familiar in physics. They tried things like simple dust particles, and then moved on to more complex ideas like perfect fluids, which are basically idealized gases or liquids, and even things like charged dust. The stakes here were pretty high. If any of these could mathematically create a warp bubble without breaking known physics, it would totally change the entire conversation.
Now let's talk about how they actually did this. It's really important to get this straight. This wasn't a physical experiment. Nobody was building anything in a lab. This was a purely mathematical and analytical study using the powerful tools of general relativity to see what's possible.
You can really break their process down into 3 key steps. First, they started with the known equation for the shape of space-time in a warp drive. That's what we call the Alcubierre metric. Second, they plugged in a source, saying, okay, let's pretend this shape is being made by a perfect fluid. And third, this is the real heavy lifting, they solved Einstein's field equations to see if the whole thing made sense. Is it mathematically consistent? Does that source actually produce that geometry?
Okay, and since this was a theoretical study, we have to be super clear about its limits. This research can tell us if a mathematical path exists, but it tells us absolutely nothing about whether we could ever physically engineer something like this. And keeping that limitation in mind is the only way to really understand what the results mean.
All right, so now that we get the setup and its limitations, let's look at what the data, or in this case, the mathematical solutions, actually told them.
And the findings were really interesting. When they tried to use simple dust as the source, the equations basically collapsed into a vacuum. No dust, no warp drive. But when they used something more complex, like a perfect fluid, something new popped out. The math suggested that solutions could exist that didn't need negative energy. But, and this is a big but, it came with a really weird catch. The function that described the shape of the bubble had to use imaginary numbers. And right now, we don't really have a clear physical interpretation for what that means. But maybe the most important discovery came from a place they weren't even looking. The math revealed this deep, completely unexpected connection to a totally different area of physics. What they found was that a very specific equation, called the Burger's equation, just sort of appeared naturally out of the warp drive math. Now, this equation is famous for describing how shock waves form and move through fluids. And its appearance here suggests that maybe a warp bubble is kind of like a shock wave, but a shock wave in the very fabric of space-time itself.
Now, these results are really thought-provoking, but to be scientifically responsible, we have to be extremely precise about what this research does not show.
So let's speak crystal clear. This work shows that there might be mathematical paths to a warp drive that get around the whole negative energy problem. It tells us the problem is a lot more complex than we might have thought. What it does not do is give us a blueprint for building one. It doesn't prove they are physically possible. It just suggests that the mathematical door we all thought was locked might actually be slightly ajar.
So if it doesn't prove we can build a warp drive, why does this research matter so much? Well, because it nudges our basic understanding of the problem and opens up completely new questions for scientists to ask.
And here's the real takeaway. The biggest impact of this research is how it reframes the problem. It shifts the conversation away from impossible physics because of exotic matter and toward a problem of immense complexity. It suggests the barrier might not be a hard and fast law of nature, but an engineering and complexity challenge that is just astronomical.
And like all great science, this paper creates more questions than it answers. What is the real physical meaning of this connection to shock waves? Should we start thinking of a warp bubble as a kind of controlled break, a discontinuity moving through space-time? And what on earth could a shape described by imaginary numbers possibly mean in the real world? These are now wide-open questions for physicists to explore.
So, what can we responsibly say at the end of all this? The results tell us we should probably be a little cautious about calling the warp drive impossible. Instead, this work really shifts our perspective. It suggests that maybe, just maybe, faster-than-light travel isn't forbidden by a fundamental law of physics, but is instead a problem of such staggering complexity that it's just far beyond anything we can even imagine, let alone build.